Okay. Um, how are you guys doing?
I'm doing good.
Okay.
How are you?
Pretty good.
Doing all right. I don't know how long these things actually stay up there. Okay. Um, right. So let me put these up. So in the review, um, there were some kind of partial solutions there. Right now, I'm posting the or full written out um, solutions that you can that I'll be kind of walking through. So we talk about this. Um, okay. So those are going up in a second. And so the problems that we're talking about is all so relations and the kind of beginning parts of functions. So a good um, amount of what we're talking about, some of it is there will be some computation problems. Like here's a function, find its domain and range, or domain and range for the relations. Um, Also in the review, we see that there's a couple examples of relations and figure out um, which of these named properties we have. So besides these sample problems, I'm was in the middle of finishing one before we started this, the solutions from, or some selected solutions from the previous homework soon get posted. So that'll give, I think, more examples of what a lot of proofs look like. But we can start talking about these problems. So these are the solutions that are up there. And right, so we didn't write out the problem. So this first one is saying if you have two sets A and B, and I say something, there's some like background set X. So actually, let me, so I want to change how I'm doing this. I want these review problems up here also. So I'll kind of jump between these guys. Right, so given some sets A and B, we want to show that A times B intersect X minus A times B is empty. So what this set is really saying is, I want to talk about the things that aren't in A. And to do that, we really need to have some idea of what is outside of A. So given this, a couple things before we actually start the proof. If you want to show that something is empty, so showing that these two sets are disjoint, maybe the best way to do that is a proof by contradiction. Assume there is something in this intersection, and then that gives you a particular object or some kind of thing to talk about. And then, so if you assume there is an object in the intersection, then you can start stating what you know about that object. And at some point, you'll run into some trouble. The other thing that we'll want to keep in mind, and this will be sort of insight for a lot of these problems. If you assume something is in here, you know that it's an ordered pair. So the first step can really be, for a contradiction, assume we have an ordered pair in here. And the way that we learn about ordered, or that we start to get more specific knowledge about ordered pairs, is if they're in a product that's really an and statement concerning the two coordinates, what sets you know the coordinates come from. And so that's how the proof starts. So for a contradiction, if we're assuming this intersection is non-empty, we know it's an ordered pair. So this gives us specific objects X and Y, and we can keep track of where X and Y are or aren't. So then being in an intersection means we know that it is in both of these sets. And then also being in a product means you know where each of the coordinates comes from. So if a pair X, Y is in A times B, then the first coordinate is in A, the second coordinate is in B. And the same thing in the other set, X is in the first factor of the products X minus A, and Y is in the second set B. So at this point, we're really just unpacking this definition, this big set we've defined in terms of really a lot of and statements about which elements sets belong to. But then we want to think about where we're going to get a contradiction. And if we go one step further, focusing on this, if X is in here, then in particular, X is not an element of A. And that is the contradiction. A lot of times when your proofs that two sets are disjoint, you are going to end up with an element being both in and not in a particular set. And that's what we have here. From the first part, X is in A. From the second part, we get that X is not in A, and that's a contradiction. So our initial assumption that we had something in the intersection was incorrect, so they are actually disjoint. Questions about this problem? Okay. Let's see. The second set, or the second problem, is make a product. It's all ordered pairs whose first coordinate come from the first set and whose second coordinate comes from the second set. And so our first coordinates are 1, 3, and 5. Our second coordinates are 1, 2, and we make all of their combinations. So 3, prove that if A is a subset of B and C is a subset of D, then A times C is a subset of B times D. So here, we again want to combine the proof strategies we've been using for a while with now things are products in ordered pairs, and how do we prove that and use those different things. So being a subset proof, we know that we need to say, take something in here and prove that it's in here. That's what it means to show something as a subset. If you're in here, you're an ordered pair, and your coordinates come from these two sets, from A and C. Along the way, we need to use our assumptions that A is a subset of B and C is a subset of D. So these, since they're not products, these don't apply to the ordered pairs. These are facts that are on the coordinate level. So if we ever get some object in A, we know it's in B, and if we ever get some object C, we know it's in D. And if we have an ordered pair in A times C, then we have two coordinates that are in A and C. So, and we have two facts about if things are in A or C. So that's kind of the broad strategy. That would be some of the scratch work that you're working out. You're starting with something in here, that something is an ordered pair. You know where the coordinates come from, A and C. Then you go back and say, oh, hey, I know something is in A and I know something is in C. And this lets me learn more about where those objects belong to. And that'll get us to the end here. So figuring it out, you have to, there's more that goes into it than the proof, which is actually somewhat short. But we do need to kind of keep track of the some of the starting here, use the assumption, and then go back to the conclusion. So proving it's a subset, that means start with an element in the product. We need to prove it's in the other product. But when you know that a pair is in a product, really the first thing you do is say, I know where, if I know this pair is in this product, then I know where its coordinates are. X is in A and Y is in C. And if you know that two elements are in these sets and you know these subset relationships, that lets you say that X is also in B and Y is also in D. And that step not only uses these assumptions you're given, but also you want to head towards that the pair is in B times D, and that lets you move from A and C to B and D. Then after we've learned this about the coordinates, we start repackaging. So we know these two particular elements are in B and D, so their product is in B times D, and that was really what we wanted to prove. Assume it's in one product, show it's in the other product. This XY was arbitrary, so we could have done this for any pair in A times C, so that means that this subset relationship is true. Questions about this proof? Oops, and I just hit it. Okay. So I think a lot of the first kind of the beginning ordered pairs product stuff is a combination of using the proof techniques that we talked about before, but then also knowing how to use the fact that we have these products and ordered pairs inside of them. So there's definitely going to be some problems like this on the exam. I give you a relation and you need to tell me what properties does it have, either prove that they're true or provide a counterexample. So all of these statements are universal. They all say for every element or two elements or three elements, something is true. So a counterexample is going to be find specific objects, either one thing not related to itself, two things related one way but not the other, or three things where you can't do the transitive thing. So you need to come up with these elements and show that whatever property doesn't actually hold of them. And if it helps, it can, when you're first trying to figure out what this relation looks like, is to pick a couple pairs and see if they're related or not, just to get a feel for what things are related to what other things. So for instance, you know that, so maybe 4 times 5 equals 20. So 4 is related to 5. If you try some other pair, like 3 times -3 is -9. So 3 is not related to -3. So you can try a couple out just to see what's kind of going on. But at some point you have to prove these general facts, and so that's what we'll do. So let's try this out. Okay, there's a little extra commentary there. So reflexive always means everything is related to itself. So reflexive proofs always start, take an element of the set your relation lives on, and you have to prove it's related to itself. And so here you need to think about, well, if we have x in both of these places, that's x times x, which is x squared. And squares are always greater than or equal to 0. Maybe the better way to write this would be kind of flipping the order. So you say, what happens if we multiply them together? Well, that's something squared, and squares are always greater than or equal to 0. So you are using a fact about real numbers, that squares are always positive. And that turns out to be why everything is related to itself. So this x that you picked, it satisfies this property, so it is related to itself, and x was arbitrary, so it's reflexive. Symmetric means take any two things and then assume that they are related, keeping track of the order in which they're related. So we take two numbers, x and y, and assume they're related. X is d related to y. And in this proof, we have to keep track of the order in which we write things. So this means that x times y is greater than or equal to 0. But we know that multiplication is commutative. It doesn't matter the order you multiply things. So the quantity we get here is the same as if we multiply the other order. And if the first one's greater than or equal to 0, the second one is 2. And so this move that our relation is based on multiplication, and we can multiply in whichever order we want and get the same thing, that lets us reverse the numbers here. And if y times x is greater than or equal to 0 in this order, then y is related to x. And so we said for any pair, if they're related one way, they are related the other way, and that proves the for all statement. So every proof that something is symmetric is going to begin like this, basically. Maybe with a different set, but it always starts take two things and assume they're related, and then you want to get to they're related the other way, and then D is symmetric. So it's all about filling in the gap. What is it that allows you to change the order in which they're related? if you want to check it's transitive, it turns out that it's not. 9 times 0 is 0, which is greater than or equal to 0, and 0 times -4 is 0, that's greater than or equal to 0. But 9 times -4 is -36, that's not greater than or equal to 0. So this is what being transitive explicitly does not let happen. We have a pair that's related, one object related to a second, the second is related to a third, but we can't go from 1 to 3. So this thing isn't transitive. What is also, or what can be kind of instructive is, what happens if you try to prove this? So xy is greater than or equal to 0, and yz is greater than or equal to 0. What about xz? So that's really the question. If you try to prove this is transitive, how do you go from these two facts to this fact? And a kind of problem is that if you try to like divide both inequalities by y, you get x. Okay, these are supposed to be equal to, but well, I'll put it in less than or equal to 0, and z greater than or equal to 0, or both reversed. Reversed because multiplying or dividing, it matters if you divide by something positive or negative. If you divide both things by positive number, then the inequalities stay the same. If you divide by a negative number, the inequalities reverse. So this can get you somewhere, but a problem here is, what if y is 0? You can't do this move if y is 0. And at that point, if you're trying to decide if it's transitive or not, if you try to prove it and there becomes, or you find a stumbling block that you can't seem to get around, that maybe indicates that what you're trying to prove isn't true, but maybe you can try to exploit that stumbling block. So on our way to dividing this y out to tell us about x and z, and if we could get here, we'd be done. Because if two things are greater than or equal to 0, then their product is greater than or equal to 0. And if they're both less than or equal to 0, their product is greater than or equal to 0. But we can't get here because we can't always divide by 0. And that's what happens here. If they're both related to 0, then that lets you go from this positive number to this negative number, and their products aren't going to be, their product isn't greater than or equal to 0. So if you're given this situation, decide if it's true or not. If you try to come up with a proof, either you succeed and that's great, but if you get stuck somewhere, maybe try to turn that place where you're stuck into a counterexample. So it's not transitive. Just a couple extra facts which weren't included in there, but could be good kind of tests. No, I shouldn't say test because that makes you think it might be a test problem, but good more practice with this example. If you take the definition and change less than or equal to or greater than or equal to just greater than, it becomes transitive. And that proof that we had, it can, you can make it work. Because if the product is greater than 0, the two numbers can't be 0. So you can make that proof work. But in this case, if you change this, it's not reflexive because 0 isn't related to itself. So this proof that we had up here, x squared is x times x, it's greater than or equal to 0, but you can't say that it's greater than 0 because there is a number where if you square it, you don't get a positive number. So as a sort of combination of these two, if we use the strictly greater than inequality and we only talk about non-zero numbers, then this actually has all three of these properties. It's an equivalence relation. So reflexive is proved like this. Symmetric is proved like this. Transitive is like we had written there. And it turns out there are the two equivalence classes, the positive numbers and the negative numbers. So if you want to test yourself a little bit more, you can try to prove these facts here. So what are these other problems? Or before we move on, questions about this number 4 here? So the next two are given a finite relation on some set. Draw the directed graph. So that's the picture with arrows going between or representing that the initial point is related to the target point. In the first case, also find the inverse. In the second case, check if it has these properties. And in this case, there's not really work. It's just look and see if you can find if they have any of these properties or not. Okay. So here's both of them. So you have to look back and see that these pictures are right. For the inverse, this is, you just flip all the pairs. So this is the relation where we've reversed every pair. Let me try to get both these on here. Yeah, okay. So then if we look at this relation and this picture here, 1, 1 gives us the loop, 1, 2, and 2, 1. So these points are related both directions. So we have this double arrow. 3, 2 says go from 3 to 2. 4, 1, that should be a comma, not a dot, goes from 4 to 1. So that's where this picture comes from. And in this case, it doesn't actually have any of the properties. It's not reflexive because most or 3 of the points don't have any self loops. It's not symmetric because these 2 arrows don't go both ways. And it's not transitive. So transitive, so Y would be, you can go 3 to 2 and 2 to 1, but you can't go straight there. And you can go 4 to 1 and 1 to 2, but you can't go straight there. So if you were given a picture and you wanted to sort of verify, I guess that's what's happening here. If you want to say why it's not transitives, reflexive or symmetric. You want to point out the specific pairs. So in this case, so we have both of these. So given 6 here, the first 3 say have all of the self loops. 1, 2, 2, 1 says we have this edge both directions. 2, 3, 3, 2 says we have both edges this edge both directions. And then it is reflexive because everything has a loop. Symmetric because these 2 edges go both ways. And so symmetric means if there is an edge, it goes both ways. The fact that there's no edge here doesn't affect being symmetric at all. But not transitive, that is a property it fails to have. And if we want to say why, then we can say that 3 is related to 1, and 1 is related to 3, or no, 1 is related to 2, but not 3 related to 2. So we can go this step and this step, but we can't go straight there. Questions about either of these guys? So 7 is prove that R, so R, first we want to think about what it actually is. So it's a relation on n times n, meaning this is relating pairs of natural numbers to other pairs of natural numbers. Those are the kinds of things being related. But the way in which they're related is you look at their coordinates. And this is a little mixed up. It says that A plus D, the first coordinate of the first one plus the second coordinate of the second one is equal to the first coordinate of the second one plus the second coordinate of the first one. So we want to prove this is an equivalence relation. So down here, I gave one way of doing it. Reflexive is saying if you have a pair X and Y, so you're taking something in the domain or in the underlying set n times n, take something in here which is itself a pair. So you take an X, Y, and you want to know if it's related to itself. Well, that so if XY is going to be related to XY, means that the first coordinate plus this second coordinate is equal to this first coordinate plus this second coordinate. And if you write that down, what you get is that you have addition in these 2 directions, or in these 2 orders. And since this is true, every pair is related to itself. I also walk through the key kind of fact if you're proving that it's symmetric. Here you take 2 pairs and assume they are related this way. If you flip which side of the equal sign they're on, this means they're related the other way. Transitive is a little more complicated. Your assumptions of which ones are related give you these 2 equalities, these 2 equations. If you add them together and then cancel out the D and C, you're focusing on A, B, and EF, you have A plus F here, and E plus B here. So another way of doing this, which if you notice it, makes things easier, is for this relation, two pairs are related if their coordinates add up in this way. But if you subtract things, so you might think like, I don't know why they're mixed up like this. Let's try to put the two coordinates on the same side. If you do that, so subtract B and subtract D, what you get is that two pairs are related is if first coordinate minus second coordinate is the same for both of them. And this way, I think, makes it a lot clearer that this is going to be an equivalence relation, because you're saying two pairs are related if when you compute this quantity, you get the same thing. And so that kind of says this relation is based on things being equal, and things being equal, that is an equivalence relation. So here the proofs are easier. If you take a pair, subtracting the coordinates is the same thing, so it's related to itself. Being symmetric, if they are related one direction, their differences are equal, you can change which side of the equal sign they're on, so they are related the other way. And being transitive, the assumption that you can go from AB to CD and CD to EF means that their differences are equal and these differences are equal. But then using that equals is an equivalence relation. We can go, well, A minus B and E minus F are both connected to, need a better color than that, green, are both connected to C minus D, so then they must be equal. And if their differences are connected, then the pairs are related. So if you can find a different way of understanding the relation, that can help a lot. In this case, a little bit of algebra gets us to this better version. In this D example we talked about, no, never mind. So in the D version, this sort of alternate, this kind of different variation, it's defined in terms of a product being greater than 0. Another way is two things are related if they have the same sign, either they're both positive or both negative. And that way, I think, is easier to prove it's an equivalence relation. But you'd have to verify that that's actually what's going on. In this case, a little bit of algebra turns it into this sort of mixing the coordinates up to the coordinates from the same pair are on the same side, and that's a little bit easier to work with. So the last few were talking about functions. And so here we'll want to remember, or we need to remember what it means to be one-to-one onto those things. So one-to-one means different inputs go to different outputs. So a way of showing you're not one-to-one is an exists proof, saying find different inputs that go to the same output. And so in both cases, that's what we're looking for. If you play around with this, I think especially in this case, there are several ways you can show it's not one-to-one. Maybe the easiest is that there are multiple inputs that make it 0. So actually, this function has 3 zeros, 1, 0, and -1. And so how we're understanding that now is there are two different inputs, 1 and -1, that get mapped to the same place, and that's what can't happen if you're 1-to-1. The only 1-to-1 means the only way you are sent to the same output is if it's really the same input. In 9, if we think about this, so this is a sequence, this alternating sequence. If you put in natural numbers, it bounces between 1 and -1. So in particular, you put in 0, you get 1. If you put in 1, you get -1. If you put in 2, you get 1 again. So those are two inputs which give you the same output. And so this function is actually really not 1-to-1. There are only two possible outputs. So the range is these two numbers, 1 and -1. And all of the even numbers get sent to 1, and all the odd numbers get sent to -1. So it's not even that there are different inputs going to the same output, but each output gets used infinitely many times. So it's really not 1-to-1. 10 here, this is, in some sense, the kind of problem that you could have seen in pre-calculus. It says compose these two and find their domains. So the largest domains contained in R, meaning you could say, well, what about like complex numbers or something like that? No, we're saying if you're only allowed to put in real numbers, what is the largest possible domain? Because you could restrict the domain. You could make it finite or maybe only allow natural numbers or integers in here, but we're looking for what's the largest possible set. And so forming their composition, if we're given formulas for them, that really means take the formula for G and stick it in to the spot where the variable is in F. So F composed with G says take 2x plus 2 and stick the formula for G inside of X. That simplifies, or really we multiply the 2 on top to get 2 over x minus 2 plus 2. And if we're looking for what the domain is, well, we can't divide by 0, so we can't put in 2, but that's the only problem. So the domain is everything, or the largest domain you can give it is all the reals except for 2. The composition the other way says G composed with F, take F, 2x plus 2, and stick it in for this x inside of G. 2x plus 2 is going in right there. We don't need that little arrow anymore. So 2x plus 2 minus 2. Now we get some cancellation, 1 over 2x. So in this case, we can't put in 0 because that would make the denominator 0. But every other real number is okay. Something which is new, or kind of a little bit new, but also a little bit familiar, is 11 says, here's this function from the real numbers to 0 to infinity, so the positive numbers, given by e to the x minus 4, show this is a 1-to-1 correspondence. So a 1-to-1 correspondence means that it's 1-to-1 and onto. So we have to remember what those mean, and then also how do we prove them. So 1-to-1 means, and the part to kind of the general part to take away is assume that for your function that the outputs are equal. You need to prove that the only way that can happen is if the inputs were actually equal. One-to-one is also thought about as saying different inputs go to different outputs, but for proving something is one-to-one, it's often easier to use this direction, because if you know things are equal, then we know algebra to say if these things are equal, then something else is equal, and then something else is equal. And that's really how we proceed. If the outputs are equal, then we have, forget those for a second, we have a formula. So we have two inputs, x and y. So if you put them into this function, you get the same thing. So e to the x minus 4 equals e to the y minus 4. But we know some algebra. And really, the algebra we know is that we know certain functions are one-to-one. So here, we're really using that the exponential function is one-to-one. You have these two different inputs, and you get the same output. So the inputs must actually be the same. Or solve it by taking the natural log of both sides, which is, we'll see, applying the inverse function, which is something that we've talked about inverses a little bit, but we'll kind of say a lot more on Tuesday, but that won't be on the exam. So we can take the natural log to cancel these e's, x minus 4 equals y minus 4, add 4 to both sides, that keeps things equal, so we get x equals y. And that's what we wanted to do. Assume they have the same outputs, show that it was actually the same input. For proving it's onto, you take any output. So here, actually, this is a little bit of a typo. It should really be take y in 0, infinity. So take a y in the target space, meaning, okay. So take a y in here, show that for everything in the target space, there is going to be some input which is sent to it by the function. So for any positive number, we need to find a real number that gets sent to it. I wrote a little bit more here. I was running out of space in the handwritten stuff. Right, so for y in 0 to infinity, find an x. So if you evaluate x or f at the point x, you get y out. So what that means is you are given this y, you want to find an x which solves this equation. So you actually do the work of solving this equation. Take the natural log. Here, and this is important, you are allowed to do this because your y is from 0 to infinity. If we changed this problem, so we said that this function was from r to r, it would no longer be onto, because there would be real numbers which aren't the output for any input. If we change this to r, then there's no input, so we get -1 out of this. And in this proof, we're kind of seeing the reliance on that we're only talking about positive numbers, because in order to find the x, which gives us our y, we want to take a natural log, and we can only do that if we started with a positive number. Well, since it is positive, we can take the natural log, we get x minus 4, add 4 to both sides. So that's where this x comes from. So here I just kind of jumped to it, but you really set y equal to f of x and solve that equation for x. Then you check, and this is, If you solve the equation, this is predictable, but you can check if you put this expression into the function, you're going to get the y out that you started with. So f of x means take the net, it's a little bit easier to see here. If you put this expression, natural log of y plus 4, into the function, then that's e raised to the natural log of 4 plus 4 minus 4. And then what will happen, if you form this the right way, is things start to cancel in pairs. This 4 and minus 4, those are gone. E and the natural log, those are gone. And so you just get y. So this means for any positive number, you can find some number which outputs that. So the function outputs that y, and we actually constructed it. This is the input which gives you this output. The last one is a little bit more, but any questions about this problem here? Like proving something is a one-to-one correspondence. So I would say it's the steps involved are the kinds of things that you're familiar with, but the way you write it out, you want to be clear why you are doing these steps and what, after you've completed these steps, what you have actually shown. So the last problem is a proof involving functions. So suppose that f and g are functions from a to b, then prove that their intersection is a function from c to b, where c is all of the points in a, so f and g give you the same output. So in here, there's to unpack this, what we're saying is we're thinking of f and g as sets of ordered pairs. So we're saying f and g are subsets of a times b with the specific function property, meaning every input has exactly one output. And so what we're saying is, here are two subsets of a times b with a certain property. Show that if you intersect these sets, which is f intersection g, that also has a given property. So, so I guess when we intersect them, f intersection g is at least a relation from a to b. F and g are subsets of a times b, so their intersection is also a subset of a times b, so it is a relation from a to b. But we want to show that it's actually a function as long as we use this set C as its domain. So if this is what we want to prove, being a function, there are two parts. There's an existence part and a uniqueness part. Existence means for every input, so for everything in C, you can find some B which is paired with it. So you can find a B, so CB is in this relation. But then also, we want to show that for every C, there's at most one B. So the way that's proved is, given a C, assume it is paired with two different B's. Show that those B's you took are actually equal to each other. So we have these two halves, and these halves are fairly typical of what it looks like to show something as a function: existence and uniqueness. So to show something as a function, take something from the domain and show you can find an output which is paired with it. So if we take a C in C, that is this set right here. Well, if we're trying to find an output, we have these two functions around, and we should think about what these two functions do to our object. So we have a thing here in A. We have two functions on A. What do they do to it? But because of where this C came from, the two functions have the same output for this C. So G of C and F of C are the same. Let's call this thing B. So these two pieces of notation name the same object. Let's give that a simpler name, B. Then what we can say is that the pair CB is in F, because this B we said is equal to F of C. And the function looks like pairs input output. So because this B is the output under F of the input C, the pair is in F. Using essentially the same reasoning, the pair CB is in G, because G is the object that we can also call G of C, which is given input C, G of C is whatever output the function G gives you. And B is another name for that output. So CB is in the function G. And then we have that this single pair is in this relation and this relation, so it's in their intersection, which is what we really wanted to do. We said, here's this relation. We're saying for anything in its domain, show we can find some output, so the pair input output is in this relation. And that's what we did. Given any input, we found something, so the pair is in the relation. And that's existence. And if we don't have a formula, which for these more abstract problems we don't, you really have to, the only thing you can do, like what you have to do, is you have to think about, we're looking at ordered pairs being in relations with some kind of special property. So for the uniqueness, here we're saying take an input. We know it has at least one output. That was the first half. Show that it can have at most one output. So that means pick a C in C and assume it appears as the first coordinate of two different pairs. So assume CB1 and CB2 are both in the intersection of F and G. Then, in particular, because it's an intersection, these pairs are both in F and they're both in G. In fact, it's good enough to be in one of them. Because if they are both in F, well, F is a function, and the property of functions is if you have a single first coordinate paired with two second coordinates in a function, those second coordinates can't be different. They actually have to be equal. And that was really what we wanted. We said, here, take these two pairs with these different second coordinates. We want to show that those second coordinates are actually equal. And the way we do that is by saying, if they're in this relation we're looking at, then they're actually in F, which we know is a function. An additional fact, which wasn't part of the problem and I didn't prove here, but which could be good to try to figure out, is that C is the largest subset of A on which F intersection G is a function. meaning if you take any subset, if you try to include anything not in C, you won't be able to find a pair for it in F intersection G, because C is the place where F and G agree. If you take something not in C, then F and G give you different outputs, and then then you won't be able to find a pair that's in both F and G. Questions about any of these problems, or kind of anything that, as long as you're here, that I can talk a little bit about? Okay. So this recording is going to go up on YouTube. If there's anything you feel like you want to listen to or watch again, the solutions to the homework problems that were turned in last week are also going to be posted tonight. So you can look through and see which of those problems, or any problems that you want to know how they're worked out. There will be, I guess, the problems I grade, the solutions will be up, so you can see what some of those proofs look like. Yeah, so thanks for stopping by. I can stick around for any questions, but if not, I'll see you guys tomorrow in class.